Okay, let's talk about how to create the first and second derivative sign charts when we're given a graph of the first derivative. So, when you're creating the first derivative sign chart, it's going to be like you're superimposing that x-axis onto this graph because you're given the graph of f prime. So to get the f prime sign chart info, you just directly read this graph. So I can see the graph hits 0 here when x is a -1, and again here when x is a 2. So the height of the graph is 0 at those 2 points, and those points become the partition numbers of the f prime sign chart. And then this region of my sign chart that goes from -infinity until I hit -1, those inputs create these outputs of my graph that fall below the x-axis. So I'll indicate that by putting negatives along that region of my sign chart. And then the other two regions from -1 to 2 and then from 2 to infinity correspond to the graph being above the x-axis. So I'll indicate that with plus signs in those two regions of my sign chart. Okay, so I'm going to lasso this and just move it down, and there is my first derivative sign chart. Okay, now let's do the second derivative sign chart. Now, this sign chart really gets confusing because most students have trained their brains to think second derivative is concavity, and they try to read the concavity of this graph. So this graph is concave down until I hit this point where x equals 1, and then it shifts concave up. But I'm not going to put 1 on this sign chart. I'm not going to put that as a partition number with concave down and then concave up, because the second derivative describes concavity of the f of x graph. But we don't have the f of x graph, we have the graph of the derivative. So we'll need that concavity information later when we go to sketch the f of x graph, but I'm not going to read the concavity off this graph. So how do I get second derivative information off a first derivative graph? Well, we're going to need to think about the second derivative being the derivative of the first derivative. We're given the graph of the first derivative, so the slopes of the tangent lines are going to describe the second derivative. Remember that a derivative is an instantaneous rate of change. We used the limit to shrink the distance between 2 points until it was a single point, and it described the slope of that tangent line. That's what the derivative does. So since we have an f prime graph, the slope of the tangent line is going to describe the derivative of f prime, and the derivative of f prime is the second derivative. So here I can see that my tangent lines are pointing up. They're pointing up, they're pointing up, so that second derivative is going to be positive up until right here where my tangent line goes horizontal. That tells me when x is 0, the slope of the tangent line is also going to be 0. So the second derivative is also going to be 0. And then my tangent lines start pointing down until I hit this point right here where x is 2. The tangent line goes horizontal again. So this derivative of this graph, which would be the second derivative at 2, is going to be 0. And then those tangent lines go positive again. So my partition numbers on my sign chart down here are going to be where the tangent line goes horizontal, and that happened at x equals 0 and x equals 2. So my tangent lines went up, up, up until I hit x equals 0, then it went horizontal. So that's a second derivative would be 0 there. Then the tangent lines went down, down, down. I'll put negatives to represent that until I hit x equals 2, where the tangent line went horizontal again. I'll represent that with a 0. And then the tangent lines went up, up, up again. So I'll represent that with plus signs. So now we have our sign charts. We read the graph of the first derivative to get the first derivative sign chart and the second derivative sign chart. So now I'm going to completely ignore this graph and just use the sign charts to think about the graph of f of x. Now, maybe I shouldn't completely ignore the graph of the derivative yet. I can use some algebra knowledge to give me an idea of what the f of x graph should look like. For example, I know that the shape of this derivative graph is cubic. That means that the f prime rule, whatever it is, had degree 3. I mean, it's probably not x cubed, but the degree would be 3. So what we can do is we can think backwards and say, okay, what would the degree of that original function need to have been so that when I do my power rule, you know, that says drop the exponent down and then decrease it by 1, I would end up with an exponent of 3 for the derivative. Well, that exponent would have to be a 4. So that means my original graph, my f of x graph, should be quartic. So either both ends are going to point up with at most 3 turning points, or both ends are going to point down. I also know from my algebra knowledge that when I read the graph of the derivative from left to right, I'm pointing up. So that would be a positive leading coefficient. So I would know that the original graph would also have, the f of x graph would also have a positive leading coefficient. So my n should point up. So my f of x graph should look something like this, like a W shape, kind of a curvy W, no sharp points, right? So let's just see if that's what we get from these sign charts that we created. Okay, so now I'm going to ignore this graph. I'm not going to look at it because it might confuse me. And I'm just going to lasso these sign charts right here. And I'm going to move them down this way. And we'll use them to graph our function, f of x. Okay, so let's do that. I'm going to start by labeling the y-axis f of x because we're drawing the f of x graph now. And I want to make sure that all my partition numbers get on this x-axis right here. So I need to have a -1. I need to have a 0. Well, that's at the origin. And I need to have a 2. Okay, we can do more tick marks than that, but we need at least those partition numbers on there. Okay, so now we go to our first derivative sign chart. What information about the f of x graph does the first derivative give us? Well, that's going to tell us about the local extrema of the f of x graph and the slopes of the tangent lines of the f of x graph. So I can see that the tangent lines start pointing down, then they go horizontal. They hit 0 when x is equal to -1. Then my tangent lines point up. And then when I get to x equals 2, the tangent line goes horizontal again. It's a slope of 0. And then the tangent lines continue to point up. So I'm going to have a local min when x equals -1. And when x equals 2, my tangent line goes horizontal, but it's not a local extrema. So let's go mark those points on our graph. Now, this is a possible graph because I don't know exactly how far down to plot that local min. All I know is that it needs to line up with the partition number or the input x equals -1. So I can put my local min anywhere on that horizontal line that lines up with x equals -1. So I'm just going to really exaggerate and place it way down here. Again, I could have placed it up here. I could have put it right on the x-axis, like anywhere along that horizontal line. But I'm going to place it down there. Okay, so I'm going to label this as my local min. And I'm going to emphasize that my tangent line went horizontal there. Just sketch that in. Okay, and then I also need to place the x equals 2 point somewhere lining up with the partition number. X equals 2, and I need it to be above this local min. So basically, anywhere in this region, I can plot the point above x equals 2. I don't know. I mean, I could plot it down here, but the closer I get to that min, the harder it'll be to exaggerate concavity later. So I'm gonna place this point pretty high. I'm gonna place it, I don't know, up here. Again, it's just a possible graph. As long as my point lines up with 2 and it's above that local min, we're good. But I don't know, I'll put it there. Okay, and I'm gonna mark that my tangent line does go horizontal there. I might even put the words horizontal tangent line just to be super clear. Horizontal tangent, but it's not a local min or local max. Okay, that's why it's probably important to mark horizontal tangent line there. It might be more subtle. We're at a local min or max where you have that dip or valley, and you know, that mountain or that valley, it's more obvious. Okay, so we have that labeled. Now, my second derivative sign chart tells me about the concavity of the f of x graph. Okay, so that's how I'm going to connect these points with the curvature here. So I'm going to go from concave up to concave down and then back concave up. So I'm concave up until I hit x equals 0. Okay, so 0 is what we call an inflection point here. Because I'm changing from concave up to concave down there, my concavity changes. So I need to locate that inflection point. And again, as long as I line that inflection point up here with x equals 0 somewhere, and it's above this local min and it's below this horizontal tangent line, so as long as it's in this region somewhere, that should be just fine. I don't know. I'm going to make it right at the origin. Why not? So I'm going to put my inflection point right here. And then I have another inflection point when x equals 2, but I've already plotted that point. I've already made that decision, so I don't have to locate that inflection point. I just need to connect these points with the right concavity. So I'm going to start here with my concave up region. So concave up from, let's see, and I don't go vertical anywhere, right? No vertical tangent lines. Okay, so I'm going to be concave up in here, so something like that, and I have to hit this local min and bounce back off. Okay, and then I'm going to switch and go concave down between x equals 0 and x equals 2. So concave down, and I need to make sure I hit that horizontal tangent line there. So I'm really going to emphasize that horizontal space. I'm even going to label this concave down just to make sure it's concave down to the reader or to the grader. And same thing here with the concave up. Okay, and then I go back concave up from x equals 2 to infinity. And again, I'm going to really emphasize that I went horizontal there for a minute. I'm going to exaggerate that and then pop it up, concave up. I don't really have to exaggerate it too much since I labeled it as horizontal, but just to be safe. Okay, and there we have it. We have our graph. And if we want to go back and make sure that our tangent lines that were described in the first derivative sign chart match my graph, we can do that. So my tangent lines need to go, let's see, they need to go down, down, down till I hit x equals -1. So I can see my tangent lines went down, 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 down till I hit x equals -1. At that point, I went horizontal. My first derivative was 0 there. So that matches up my sign chart. Then my tangent lines are going to go up, up, up till I hit x equals 2. And I can see that happening. Tangent lines go up, up, up. And they're still going up. They're just leveling off. And then right here when x equals 2, my first derivative is 0. I have that horizontal tangent line. And then my tangent lines continue to go up. So up, up, up. Yep. So the graph I created is matching the tangent lines, the slopes of the tangent lines for my f prime chart, and it's matching the concavity from my second derivative chart. Okay, these take a lot of practice, y'all. And reach out for help from tutor, from me, talk these ideas out. If you're ever unsure if your graph is correct when you're doing a MyMathLab question, just shoot me a picture. Just take a picture, email it to me, and I can give you thumbs up or I can point you in the right direction.